Welcome to the public lecture this afternoon, organized by the Institute for Mathematical Sciences. My name is Tong Chitat. I'm the director of the Institute. This afternoon, the speaker is Professor Hugo Parlier. Parlier graduated. Parlier is graduated from the École Polytechnique in Lausanne, and is currently National Science Foundation Professor, Switzerland National Science Foundation Professor at the Institute, at the university. His research interest is in the area of low-dimensional geometry and topology, and has done outstanding work in these areas. However, Professor Parlier is also well known for his many activities in outreach involving the teaching of mathematics, or introducing modern mathematics or mathematical research to high school students, to high school teachers. And he has been involved in quite a number of such programs in both Switzerland as well as in the United States. For example, he has taught a number of times in the city of New York courses, mathematics to high school teachers and to students there. And something that is not widely known, at least not to me until today, is that he's also an outstanding tennis player. He won the junior championship tennis as a young man in the Netherlands. Although maybe we didn't see him in the Olympics this time, although he's here. So this afternoon he will give us a talk called From the Puzzle to the Moduli Space. Please welcome Professor Parlier.
Thank you very much for that kind introduction. I can't begin to tell you how honored and happy I am to be here. I can try, but then that would take the rest of the lecture. So I'm not going to. But I'm really very excited to be here and give public lectures for this type of occasion, and in particular here, at the occasion of this very nice conference. And there's many motivations for trying to explain what it is we do as mathematicians to the outside world. But so as a child, of course, I didn't want to become a mathematician. I wanted to become a tennis player. Right. And well, before that, I wanted to be a dolphin, but that's okay. Okay. But one of the reasons I didn't want to become a tennis player, I did want to become. One of the reasons I didn't want to become a mathematician, even at an elder age, is I didn't know that mathematicians existed. Right. And maybe some of my colleagues, there are lots of my colleagues here. Maybe some of them have encountered similar situations where people are surprised that mathematical research actually exists. Right? Oh, but everybody knows dolphins exist, and tennis players, especially in Switzerland, we're very aware of tennis players, but not so aware of mathematical research. And so what I want to talk about today is partly part of a sort of a lifelong project to explain what it is I do at the office to my wife. Right? And I want to share some of this for you. So, of course, I'm not the first, and Paul Halmos has this famous quote where he was saddened to know that people didn't know that mathematical research existed. And so part of this project is going to be about, and part of what I'm going to talk about today is going to be about this project called Mathema that I worked on with Paul Turner, another Paul. But before getting into that, I want to illustrate what I want to talk about today by something that everybody in this audience probably has seen before and knows, and that's a Rubik's Cube. Okay, so this is a Rubik's Cube. Right? That's a larger Rubik's Cube. And what can we say about Rubik's Cube? Lots of things. Okay, you could probably give a year-long course on the Rubik's Cube in mathematics. But what I want to talk about today is some geometrical aspect to Rubik's Cubes, which is the following. So I want to have a way of measuring how different two different Rubik's Cube configurations are. Right? There are multiple ways to do this, right? So I can put a Rubik's Cube here, and I can put a Rubik's Cube here, and I can say they're about 1.5 meters apart. Right? That's one way of saying it. Right, so that's not the way I want to do it. I want to be able to measure that by knowing how much effort does it take me to get from one Rubik's Cube to another Rubik's Cube. So I can take a Rubik's Cube configuration and I can turn it around, right? And there's different things I can do. So what I want to do is I want to say that they're some number of moves apart, their distance some number, if I can get from one to the other in that number of moves. And any way I can get from one to the other requires that number of moves. So let me be specific here. I'm going to take a Rubik's Cube here, and I'm going to allow the following moves. I can take any of the 6 faces, and I can turn them by a quarter, one way, the other way, or I can do a half turn. Those are the different moves I'm allowing. So there's 18 different moves I can do in a Rubik's Cube like this. And these are my moves. So that's the distance between 2 Rubik's Cubes. And, okay, so to encode this type of structure, something that's very convenient, and I apologize to all the mathematicians in the audience, but is a graph structure. So a graph is a very simple mathematical object consisting of vertices and edges. And these vertices or nodes, they're what's in pink here. They encode points. And an edge, you draw an edge between 2 points. You have an edge between 2 points if they're related. Okay, so of course it's an abstract notion, extremely useful. And for instance, so this is something I could do. Like I could say, okay, I want to create a graph here. So you're all nodes. All of you are vertices, everybody in this room. And I'm going to put an edge between 2 people if they've eaten black pepper crab together. Okay, it's a very Singaporean notion. Okay, so for instance, Sarah Piao Tan is connected to most people in this audience, right? But of course, vegetarians are all isolated, right? They've never eaten black pepper crab with anybody. Right? Okay, so that's one example of a graph. Perhaps more relevant to what I want to talk about. Here's an example of a graph, and this is the Rubik's Cube graph. So vertices are configurations of the Rubik's Cube, and I put an edge between 2 configurations if I can relate them by an elementary move. So here's my configuration. This guy here, this is some vertex. I did a quarter turn. It's now related the 2 by an edge. And I get a graph this way. Okay, and I'm interested in studying this graph. I want to know something about the geometry, its size, distance, that type of thing. What can I say about this graph? Okay, so one thing you might have noticed is that I'm not showing you a picture of this graph. Is that because I don't like you or something like that? No. The problem is that there's many configurations. Okay, there are roughly 43 times 10 to the power of 18 configurations. Okay, that's really a big number. Okay, this is why I'm not showing you. And so why is that so? I mean, it's sort of an abstract number at that point, right? But let me give you an example, sort of consequence, of how big that number really is. Okay, so here's a corollary to that, stating this as a mathematical statement, that humanity has never seen all possible configurations. So it's a mathematical statement, so let me prove it for you. Okay, so here's a proof, a rigorous mathematical proof. Okay, so the Rubik's Cube is about 42 years old. Okay, so Rubik's Cubes have been around for 42 years. All right? In all, there have been about 350 million different Rubik's Cubes that have been produced. All right, so I'm going to bound that number by 1 billion. I'm going to be generous with my computation. And now, suppose that those billion Rubik's Cubes were around from day 1, okay, 42 years ago. And from day 1, we found 1 billion Rubik's Cube speed cubers willing to spend night and day from the beginning for 42 years without breaks at moving configurations. Suppose furthermore that every time they make a move, they see a new configuration. So there are roughly 10 to the power 4 hours in a year. Okay, and there are roughly 10 to the power 4 moves an hour. That's going about 3 moves a second. 3 moves a second, that's pretty good. Okay, that's rough. So this is my big estimate. And what do I get when I multiply all these numbers? I'm still at 42 times 10 to the power of 17. Right? We're still off by a factor of 10. And you'll admit that I was being at least slightly generous with these numbers. Okay, so that's a corollary of the size of this graph. Okay, so humanity has never seen all configurations. So it might be hopeless to answer the following question. So here's the following question. I want to know, among all different configurations, what the maximal distance is between different configurations. I want to know which configurations are furthest apart. Right? And keep in mind that that's a big number. So I want to be able to estimate that. So one thing I'm not going to be able to do is estimate this maximal distance by hand. Okay, that I think we're all clear. Right? But people have actually managed to say something. In particular, is the theorem that's pretty recent, from 2011, that says that the maximal distance that you can have between any two configurations, with my way of looking at distances, is 20. Right? That means between any two configurations, there is a sequence of at most 20 moves, and there are configurations that require exactly 20 moves. Okay? And this is, I'm writing down theorem, but it's a mix between a bunch of math, a bunch of computer science, algorithmic aspects, and 35 CPU years, whatever that means. Right? So, right, that was lent generously to these researchers by Google. Okay, so this is what it. I mean, if you Google this, people call this God's number for some reason. And what happened was, sort of over the years, people have been working on this for 30 years, and over the years, the numbers got better and better. The lower bounds got better, the upper bounds got better, and then they finally, eventually, converged to this. Okay, what's interesting is that, okay, so remember I had this very specific way of computing distance between Rubik's Cube. Here's another way. Okay? Instead of allowing these half turns, I mean, these half turns are somewhat artificial, right? Because a half turn is just 2 times a quarter turn. Right? So what if I just allow quarter turns? Okay, well then they didn't know anymore. I'm just allowing quarter turns along these spaces. Then the answer was not known. Until recently, and more computer power, more mathematical ideas through it all, and recently, 2015, they managed to show that the diameter for this new metric, this quarter turn metric, is actually 26. Right? So if you think about it, at first you think, wait, should it be 20? Should it be higher? Should it be lower? Okay, and you realize it has to be necessarily at least 20. Right? And here's another way of computing things, right? I can say, okay, but what if I allow middle transitions? I'm allowed to move this middle one, which I physically can't do, because if I try to do this, then this other one comes with it. But supposing I had 3 hands, okay, and if I'm allowed to tilt this like this, right, this is another metric, another way of measuring it. Then again, this time the diameter is not known. It's known that it's somewhere between 18 and 20, but it's not known. Okay, so the point is that for this type of thing, we're at the very limit of what we're able to do, both from the computer power point of view and from the mathematical point of view. And again, I stress that to be able to get this was really a mix between math and computer power, not just computer power. You can't just throw CPU at this. Okay, so, all right, the Rubik's Cube is what it is. But the problem with the Rubik's Cube, when you try to explain mathematics to non-mathematicians, that if you try to tell them that math is like the Rubik's Cube, right, they might be equally, if not more, afraid of the Rubik's Cube than they are of mathematics. Right? Because you give somebody a Rubik's Cube, and there's absolutely no chance that this person, without any sort of prior training or something like that, is able to solve it like right away. Okay, it's a very difficult puzzle. So if you're trying to illustrate mathematics by the Rubik's Cube, there is that danger. Plus, you can't see the graph. Plus, you can't see lots of other things. So with Paul Turner, we came up with, and this is sort of the first excerpt from our book, we came up with a puzzle that emulates some of the features of the Rubik's Cube, but that is different. So in this case, we have squares. Okay, so n by n squares for different integers, different sizes. You have, for those who like a minimal number of squares, you have those, and then you can go on. I mean, we could have done the 1 by 1 square, but it's less interesting. And we have these configurations, just like configurations of the Rubik's Cube. We want to be able to measure distance between these configurations. Okay, so what do? This is a puzzle. So we're allowed to move these squares like this. So notice what I'm doing here is I'm making some type of horizontal swipe, going left on one of the lines. And I can go left or right, like that. And I get new configurations. And I'm also allowed vertical swipes and like this. Okay, and so I can play around with this I can do this for a long time if you want. Okay, so, and then it's a puzzle. So what's the goal of the puzzle? The goal of the puzzle is to reach some type of home configuration, which changes depending on your color thing. Okay, so this is a puzzle, and I'm going to play with the puzzle until the end of the hour. Okay, and I can try to solve this puzzle and more or less make it or not and whatever. Okay. And again, I want to have some type of notion of a configuration space and measuring distance. So of course my distance here is going to be the number of moves, minimal number of moves I need to get from one configuration to another configuration. Okay, so here's a first naive question. Given any one of these, so this is how it works, by the way. I mean, so this program, the way it works is that it puts squares in there randomly, and then you're allowed to move it. Okay, so my first question to the audience is, can I always reach the home configuration? All right, let me point out for the Rubik's Cube, if I did the same thing, what would the same thing equivalent be? The same thing would be, so I have children, and what children tend to do when they get frustrated with the Rubik's Cube is pull it apart. Okay, which is a disaster, because if you pull pieces apart and then you try to put them back, then you have even less chance of actually solving the Rubik's Cube, right? In fact, there's 12 different connected components. I mean, there's 12 different sort of sets that are reachable within movements. Okay, so you have one chance in 12 that you're going to be still able to solve the Rubik's Cube. Okay, but so in this case, we can ask the question, is it always possible to solve this? Okay, that's the first question. And we can sort of ask the same questions that we asked about the other thing. So another thing we can ask about, of course, is size. Okay, so, whoops, wrong page. There we go. So what you see here is a visualization of this graph. Okay, so each one of those green dots that you can see or not see, depending on which ones they are, they all represent different configurations. So it's not too difficult to count the number of configurations you have here. So I'll let those who want to count them. And those who don't want to count them, I'll tell you the answer. There's 1,680 different configurations that you can get, and they all represented by a star. And I can ask a slightly different question from what I asked, but maybe it's the same question, is leaving from this home configuration, which you can see there, I can sort of navigate in this. Okay, and you see the edges of the graph appear as I move around here. So here's a question. Can I reach every single one of those stars from the home configuration by making these moves? Right? In fact, that's the same question as the one I just asked you before. Why is it the same question? Because any one of these moves is reversible. If I can horizontal swipe one way, I can horizontal swipe the other way. So I can reverse any one of these paths. Okay, so it's like if you want to transit around in Singapore, all you have to do is know how to get to Harbourfront. Right? If you know how to get to Harbourfront, then you're fine. Because if you can get anywhere to Harbourfront, you want to get from point A to point B, you go to Harbourfront, and then you go from Harbourfront to that point there. Right? I'm supposing things are reversible, which is not something I should suppose apparently in Singapore public transit, because we have a bus that takes us from Kent Vale to the IMS, but it doesn't go back. So nobody knows what it actually does, but there's different theories. Okay, but I think I assume they don't throw the bus away at the end, but I don't know. Okay, so but in this case, everything is reversible. So if I can get from point A to point B, then I can get, if I can get to the home configuration, I can always get from point A to point B. Okay, so what I'm asking you really, that first question, sort of the first thing, and I do this in workshops with students, is to try to prove that you can always get from point A to point B. Okay, so what this ends up being is actually, so students, when they do this, they end up having to solve the puzzle. And if they know how to solve the puzzle each time, and they can always solve the puzzle, then they prove the theorem. Okay, just because I know some of you think, poof, it's obvious I can get from point A to point B. I don't know if any of you think that, I'm just being mean. Okay. So here's another puzzle. So this time I've added these little drawings to it, and this time the goal is to try to get back to this circle configuration. Okay, so I can sort of play the same game, and I'm just sort of randomly move these around. I mean, I don't really know what I'm doing, and sort of do this, and then that, and then that, and then... Okay, so there. Yeah, easy enough. Yeah, they didn't have this as a sport when I was growing up. I would have wanted to. Okay, so, okay, uh-oh. All right, so, hold on. All right, Okay, so this one I can't solve, and I could try to solve in front of it, but you can't solve this one. Okay, so there's a nice explanation for that, which I won't give you, but I invite you to ask me afterwards. So just to point out that this is not obvious. But the answer for the other puzzle is that you always can get from point A to point B. So once you can always get from point A to point B, then again, the question comes up as to how do I compute distances. What's the diameter of this space? It's a much simpler space. So let's look at the whole space and see what it looks like. So I'm giving you a hint here, so what the diameter is. Any guesses? No guesses. Great. It's like, let's see here, it's 12 centimeters. Oh, it's much bigger here. Okay. Right, so it's not obvious at all what the diameter of this space is. And in fact, let me point something else out. Maybe I should start low. Instead of trying to compute the diameter of the space, maybe I should actually just try to compute the distance between two configurations. Okay, so here are two configurations. Right? Very simple configurations. What is the distance between these two configurations? I mean, if someone shouts out the answer, I'll be extremely impressed. I mean, I'll be impressed that someone shouts at all, actually. Okay, so, I mean, I can try to get from one side to the other, right, and 4? Okay, that's good. There we go. I don't know how to do this. Okay, I did it in 15. Okay, so it's at most 15. Okay, so let me try again. See if I can do better. Ooh, that's better. I did it in 6. Okay, but all right, so it turns out the answer is 6. Okay, but let me show you why the answer is 6. It's not so much what the answer is, it's why the answer is 6 that is interesting. So it's at most 6, because I can do it in 6. So why is it at least 6? So let's just focus on the pink squares. Okay, so notice that on the left configuration, they're all in the bottom row. Okay, and in the right configuration, none of them are in the bottom row. So if I want to get from the left to the right, I have to get those pink squares off that bottom row. Right? Okay. So to do that, I can try different things. What do I have? I have horizontal swipes and I have vertical swipes. Right? If I make any horizontal swipe, no matter what configuration I'm in, that's never going to change the number of pinks in the bottom row. Right? I can horizontal swipe until my nose falls off, and that's never going to change the number of pinks. Right? However, if I vertical swipe, then I can change the number of pinks in that last line. Okay, but how many can I change it by? So the number of pinks in the last line, if I just focus on that, with one swipe can go down by at most 1. I can't get 2 with one swipe. Okay, so if I put that all together, to get from the left to the right, I need to make at least 3 vertical swipes. Okay. Fact 1. Fact 2, I'm going to look at the yellow squares. Okay, so what happens for the yellow squares? The yellow squares in the left configuration are all in the first 2 columns. And in the right configuration, they're all in the last column. So if I want to get from the left to the right, I need to get those yellow squares into that last column. But this time, vertical swipes are useless. Right? So if I want to do that, I need to make horizontal swipes. If I want to get those yellows in, I have to make horizontal swipes. How many do I need to make? I need to make at least 3. So I need to make at least 3 horizontal swipes, 3 vertical swipes, which means that I definitely need at least 6 moves to get from the left to the right. In fact, we've said a little bit more than the distance is 6. We've said that any path that goes from the left to the right contains 3 horizontal swipes and 3 vertical swipes. So the distance is 6. Right? So that's very good. So what does that tell us for the diameter of the space? Well, it tells us that it's at least 6. Okay. Well, that's the best lower bound I know. Okay, I mean, I sincerely doubt it's 6, but that's the best I know. All right? So you can, that's one bound on the diameter. Right? And you can try to find better bounds in the diameter. I'm sure people in the audience are absolutely capable of finding better bounds in the diameter. but that's enough. An upper bound, I can get an upper bound too. I have this algorithm for solving it, which you sort of saw. Right? If I quantify that, I can get upper bounds as well. So sort of the current state of affairs is that we know that the diameter is bounded somewhere between 6 and 13. Okay. And it'd be easy enough to program. I mean, it's not that it's impossible to do. We're talking about 1,680 configurations, not 43 times 10 to the power of 18. But, I mean, we like to play around with it and try to figure it out. Right? Work around with it. And, of course, there's many variations. I mean, I could always do the 6 by 6 chroma square and try to get the bounds on the diameter of that, or the 5 by 5. And here's another variation, which I find even more interesting. Okay, so here's another variation. All right, so this one, again, the configuration space, the vertices of this are the same. So I have 3 by 3. In this case, they're just arranged in disks. But the moves I'm allowed to make are slightly different. So I can make this move like before, and I can make this move like before. But I can't make the other vertical swipes, and I can't make the other horizontal swipes. But what I can do is I can make these diagonal swipes. All right, so we have a new game. This game's more fun. I mean, can we always solve this game? Same questions. What's the diameter? So you can make variations and then try to prove things about them. But the point is that this is sort of illustrating that very quickly you reach sort of the capacities of what either a computer can do or what you can do mathematically. Right? This illustrates this fact. Okay. Let me switch gears a little bit and go to something a puzzle that many of you in the audience have certainly seen. But I like it anyways, and I'm going to talk about it anyways. So here's the puzzle. You have well, in this case, a 6 by 6 grid, right? And you remove, this is called the mutilated chessboard problem. And you remove 2 squares. So I removed a corner in the upper left and a corner in the upper right. And I want to try to cover this by rectangles, 2 by 1 rectangles. Okay, and I've done this before, but it's this humid Singapore weather is really not good for iPads. I've never seen dominoes move so slowly in my life. Okay, and there we go. And oops, oh, how disappointing. I can't do it. Okay, so, right, so of course I'm completely incompetent because of the humid weather and everything, but that doesn't explain everything. And the real question is, why can I not do it? And there's a very beautiful mathematical reason for which I cannot solve this puzzle. So let me give it to you. I know many of you know this, but just for the fun. Okay, so we changed puzzles already. We're not like Feynman. Okay, so the board cannot be covered by these dominoes. And why can it not be covered by these dominoes? And the main idea is to do the following thing, which turns out to be a pretty deep idea, actually. Okay, I'm going to color the squares of the board, well, in this case, blue and white. All right, so it's not very clear why I'm doing that, other than it's sort of a chessboard, and chessboards are colored black and white, so that makes sense. But one thing I noticed, though, is that once I've colored it, is that the 2 squares that I've removed, which are not the same 2 squares, I'm noticing this now, okay, doesn't matter, right, they were both blue, right, in the coloring. So I've removed 2 blue squares. So I can count the number of blue squares, and I can count the number of white squares, and the number of blue squares is 2 less than the number of white squares. So there's 18 white squares and 16 blue squares. This is all very exciting. I can count squares. Okay, so what does this have to do with anything? Well, when I try to put a domino on the board, any way I put a domino on the board, I notice that it always covers 1 blue square and 1 white square, no matter which way I put a domino on the board. Okay, by the way, don't hesitate to ask questions. I mean, especially if you don't have a PhD in math. So I can cover shapes, but each shape I cover always has the same number of blue squares that the number of white squares. But the shape I'm trying to cover has a different number of blue squares and white squares. So it's absolutely impossible to cover it. Right? And okay, so that's the proof. So it's a nice illustration of mathematics for many reasons. One of the reasons is that it's very short, so that makes it nice. So you can actually show this to somebody who doesn't do math, and you say, okay, this is an example of a mathematical proof. Another reason, it has some key idea that comes into it, and with that key idea, you get all sorts of information. Right? And you generalize, you get more than what you came for. I could have removed 2 corners, but in fact, my argument works if I had removed any 2 blue squares, right, or any 2 white squares. So you get more than what you came for. I mean, I came with the 6 by 6, and this, I know exactly what happens for the 12 by 12. But you also get questions. What happens if I remove 1 white square and 1 blue square? Can I always cover it up with dominoes? Right? And this same idea actually turns out to have all sorts of other implications that I want to talk about. So think about that for a while if you haven't thought about these things before. You remove 1 white and 1 blue, and you always cover it up with dominoes. Okay, so for those of you who don't know what to do for the rest of the talk, that's what you can do. Okay, you can think about that question. All right? But one of the other things that it comes up with is something that I'm going to explain now, which is very much related to the same type of questions I was asking before. So sometimes you have shapes that can be covered by dominoes, right? For instance, had I not removed those 2 corners, I can cover that with dominoes. So there's an example of a shape that I can cover with dominoes. And once I know that a shape can be covered with dominoes, I want to know what is the space of all possible domino tilings of that shape. I mean, that's because that's my job, so that's what I do. I mean, right, that's exactly the answer to my wife's question, what is it that you do at the office all day? Is I ask, I try to do questions like that, right? So once I have a tiling, I say, can I understand all possible tilings? And here's one way, and can I compute distances between tilings? You think I'm sort of an obsessed man with this type of thing, and you're absolutely right. Okay, so how do I compute distances between tilings? How can I get a new tiling? Okay, I have 1 tiling, now I want a new tiling. Well, here's one way. I can take 2 dominoes that are side by side, right, and I can put them on their side, like that. So notice the dominoes in the bottom right. They're like this, they're horizontal, and just before they were vertical. See that? Ha! And I can go back and forth with this iPad. This is great. Okay, so I can do that. And what this gives me is, again, a graph structure. So vertices of the graph are the different tilings, and I relate 2 vertices if I can do a flip to get from one to the other. Okay, so I get a structure on the space of all possible tilings. And there's all sorts of questions you can ask about this. For instance, if I have 2 tilings of a shape, can I get from one to the other by a sequence of flips? The same questions I was asking before. Okay, that's a reasonable question. All right, so for this, for instance, can I get from any tiling of this to any other tiling of that? And I think that's a non-obvious question. In fact, there's a result. So a result essentially by Thurston that tells you that if your shape doesn't have any holes, so if it's simply connected in the language of mathematics, then you always can get from one tiling to another tiling by some sequence of flips. Okay, and I'm not explaining anything right now by saying, but that's really not obvious, but it's kind of a cool fact. So it means that if I had any other tiling of this, I can find some sequence of flips to get from one to the other. And once I have that type of result, I can start talking about the space of all tilings, and I can measure distance between any 2 different tilings and do the same sort of thing. Okay, so again, we have sort of an instance of the same type of question I was asking before. Right. And just to point out that it's not obvious, here are some examples of tilings, okay, of shapes that do have holes. So what do I notice about these? So if I look at the 2 ones on the left here, right, I've just removed a square in the middle. The 2 ones on the left, notice that all the dominoes are slightly off, like that. Okay, so I can't actually put 2 dominoes on their side. I can't do one of these flips to any of these. So on the left, you have the vegetarians. Right? They don't eat black pepper crab with anybody. Right? On the right, you have the crab lovers. Right? These have gone and eaten black pepper crab together. Right? Why is that? Because if I look at the 2 dominoes here, these ones, and I flip them on the side, I get the domino tiling there. Okay, so in this case, the flip graph of this shape is not connected. I cannot get from point A to point B by a sequence of flips. So that result must have had some type of content. Any questions? Okay, so, right. So, I mean, the problem is that the questions I'm trying to ask are perhaps too complicated. To try to answer. For arbitrary shapes, I'm trying to compute distances between tilings, trying to get the diameter of these flip graphs. Maybe that's too complicated. So maybe we should start with something much easier. Okay, some sort of simple thing. So I'm going to try to simplify this. Yeah, I wrote down maybe because I've always thought this quote was due to Albert Einstein, but apparently there's some I looked up on the web, and apparently people say, yeah, we're not exactly sure why that's attributed to Einstein. But I'm keeping his name up there because I didn't find any proof that he did not say that. Okay, so possible. So here's a simpler case. Let's take a very simple, something that we can all understand. Let's take a 2 by n rectangle. Okay, so there's a nice 2 by n rectangle there. Okay, and I want to look at all possible tilings of this. Okay, this sounds doable, right? We can do something about this. All right, and first thing we can do is we can start counting them. How many different tilings are there? So let's start counting. So the n equals 1. This is a 1 by 2 rectangle. There's exactly 1 tiling. Right? The 2, there's exactly 2 tilings. The 2 by 3, there's exactly. So I think you all see the pattern, right? Right, so we all know what the answer is for 4, right? It's, you're all suspicious. Right? You're absolutely right to be suspicious. The answer is 5. Right, it's the next logical step. 1, 2, 3, 5, as all mathematicians know. Right? So why is it, okay, that seems a little mysterious. Have I miscounted? Probably. I guess not. So why is the answer 5 to that? I mean, beyond the fact that there are clearly 5 different domino tilings of the 2 by 5. Right, there's a very good explanation for that. Here's the explanation. Again, just one idea, and then you go, oh, that's why there's that. Okay. Here's the idea. All right, so if I look at any tiling, and I look at the leftmost, what happens on the left, then I can see one of two things. I either see a tile that's like this, or I see 2 tiles that are like that. Right? There's nothing else I can see on the left. That's the only way you can cover that left thing. And of course, these things don't happen at the same time. You can't have a tile up like that and 2 tiles like that. You're not allowed to overlap the tiles. Okay, so those are one of the 2 configurations. So every tiling is either like that or like that. Which means that the number of 2 by n tilings is exactly the number of guys like that plus the number of guys like that. And the number of guys like that is exactly the number of n minus 1 tilings. And the number of guys like that is exactly the n minus 2 tilings. That means I can relate these numbers. So, for instance, for n equals 3, that means that the number of 2 by 3 is equal to the 2 by 1 plus the number of 2 by 2. So 3 is equal to 2 plus 1, that we all know. And then the next number, 4, is equal to 2 plus 3 is equal to 5. Okay, so these are the Fibonacci numbers that appear. Okay, so the Fibonacci numbers describe nicely the number of tilings. Okay, so that's a nice, yet another occurrence of the Fibonacci numbers. Okay, so let me just, for what I'm going to talk about now is this schematic point of view is going to be useful. So I'm going to replace dominoes sometimes just with lines between these little lines here. So these little black lines represent dominoes, and they cover like this. This is going to be very useful for what I'm going to do in this sequel. So I hope you understand this schematic point of view. That those 2 tilings are the same. Okay. I got sick of coloring in all the pink. I like to make black lines. It's much easier. I ran out of pink ink. Okay, so this schematic point of view. And what I'm showing you here is this is a very natural tiling that you get. This is whatever rectangle you have. I can always put all the tiles upright. This is our harbor front. This is the harbor front of tilings. Okay, so there we go. And now I want to find some way of getting between tilings. So how do I get to harbor front? Well, if I have any tiling, it's easy to see that I can get to harborfront, because my dominoes are either vertical, in which case I don't do anything to them, or they're horizontal, in which case that means that there's one underneath or above, right? And I can always put them upright. This tells me exactly how I get to harborfront. I just put all the dominoes upright. Okay, so the first thing is that, okay, so in this case, the theorem I talked about of Thurston is very clear. I can get from any tiling to any other by putting all the dominoes upright, and I'm sure to reach harborfront. Okay, and I can try to quantify this exact thing. So if I have a 2 by n, then how many guys have I had to put upright? Right? I mean, I have n tiles here. Right? When I put them upright, I put 2 upright at a time. So the number of tiles I have divided by 2 is certainly an upper bound on how long it takes me to get to harborfront. It takes me at most n over 2. Right? And that's true for any 2 tiles. So that tells me that between any 2 tilings, there's a path of distance at most n between them. Okay, just for simplicity, I'm going to suppose that n is even. This argument works for n odd. Okay, but, right, so there's an upper bound on the diameter of n even. But actually, if I think about this some more, what really could have happened here? So if I really had n over 2 moves to get to harborfront, that meant that everybody was lying down. Right? So the only time it really takes me n over 2 to get to harborfront is when everybody is horizontal. So the only time I could actually have n is if both tilings, everybody was horizontal. Right? But if both tilings, everybody was horizontal, that meant that the 2 tilings were staying at the same hotel to begin with. Okay? So that minor observation means that I can improve that bound to n minus 1. Ooh. You have no idea how much time we spend doing this, getting very excited. Woo! N minus 1. Woo! It's very weird what we do. Okay. Anyways, so we can get to n minus 1. And it turns out that this is actually not such a bad idea, because the bound actually is n minus 1. So that very naive way of getting from one tiling to another is the best, at least for certain tilings, right? And so why is that? So look at the 2 tilings that I've schematically drawn for you on the bottom. They're at distance exactly n minus 1. Why is that? Because on the left, all of them are horizontal. But none of the horizontal ones I see on the left are on the right. So to get from the left to the right, it's sort of the same argument over and over again. You'll notice I do this a lot. Okay? So to get from the left to the right, I have to make sure that all these tilings get upright at one point. Otherwise, they won't be able to move. So they all have to be upright at one point. So that's going to require at least n over 2. And to get from the right to the left, again, the same argument tells me that all the horizontal tiles have to be upright at one point. So that tells me that these 2 tilings are at distance exactly n minus 1. Okay, so the diameter of this graph is really n minus 1. So unlike in the case of the chroma squares, where I showed you these pretty pictures, at least I know the answer here. Right, so you should all be very impressed. I hope you're all duly impressed. Okay. All right, so that was the easy case, right? Now we want to get something more complicated. Okay, so, all right, I hate to show this to you, but, all right, so here's a theorem from 1961, which is very nice. So if you take, here's a very natural shape, a square, an n by n square, n even, so that we can actually tile this. You can count the number of tilings. And this number is given by this formula. So forget that this is the number of, forget this whole part, the sentence from there. All right, just this theorem, this is a whole number. That's actually an integer or an impressive result. Forget that it actually represents something, but that's actually a whole number is something that's completely mind-boggling to me. Okay, but it is a whole number, and it's exactly the number of tilings of a square. Here's another natural shape. These are called Aztec diamonds. I don't know if anybody has ever seen these before, but I've drawn an Aztec diamond for you. The order of the Aztec diamond is if you can always split it, has these symmetries. If I have an axis going down the middle and an axis going down the middle, what I'm doing is I'm counting the squares on each side. So this one here, for instance, is order 3. Okay, so I split it here, I split one of these quarters, and I look at how high or how wide that quarter is. And that's the order of the Aztec diamond. This is order 3. And so the number of tilings of an order n Aztec diamond is equal to this, which is a much simpler number, but nonetheless, this is not easy to prove. Okay, so these are two results that are what they are, but okay. And so you might want to ask, okay, we have these numbers, we want to ask the same question sort of again and again and again. What are these? How do I compute distances in this one? So this is actually what I'm going to talk about right now is a project that I did with a master's student. Right. And we tried to find some sort of way of visualizing distances between tilings. So for instance, can I get a nice formula that relates the number of flips I need to get from the left to the right? And again, our goal is to try to get diameters of recognizable shapes again. Okay, so does anybody have a guess as to, I have no idea what that is. It's very confusing. It's very difficult. I mean, again, whenever you have two configurations, it's difficult to know what the distance is, right, looking at this. I mean, if somebody guessed this number, then I would be even more impressed than, and I was already very impressed. Okay. So what we did is we used, I have to say this, we used prior work of people that used these ideas that Thurston had introduced to compute distances and functions of different things. It's not here. But so this is the basic idea, is that I'm going to use that coloring argument I showed you I'm going to use that coloring argument that I showed you before. So I'm going to color all the tiles black and white depending on whether, some coloring, some black and white coloring like this. And I'm going to use this schematic point of view. And I'm going to superimpose the two tilings. Okay, so what does that mean? So the whole segments you've seen here, those are the tilings on the left. And the dotted segments you see, those are the tiles on the right. Okay, and I put them together like that. And what this gives me, the first observation, is I get a collection of cycles. Right? These things go around. I go around here and see, these make cycles. The only thing where I don't have a cycle is here. That I had one domino on top of the other. Right? Notice they had the same domino, and I just forget about that. I just erase that. And I get a collection of cycles. The second thing I do is I want to orient these cycles. I want to give them an orientation. So, in general, this is the positive orientation, the counterclockwise. So I'm going to say that that's a positive orientation. And this is the way I'm going to orient them. Each one of the dominoes that comes on the left tiling, right, goes from a black to a white. Right, I can think of each domino as going from a black to the white. That gives me an orientation of the cycles. Right, so I put arrows on all the ones that come here, that come out of this, they go from black to white. And that gives me an orientation of the cycles. Okay, so that's how I orient these cycles. All right, and I can get a geometric object associated to these cycles. What this geometric object is something we call the filling shape. So each time I had a positively oriented cycle, so it's something that goes counterclockwise, I build something of height 1 above that. I think of this as lying in Euclidean space. That's my plane. And I build something of height 1 exactly above that, just like Lego. Right? I take a bunch of Lego blocks and I build it above. And if it's negatively, if the orientation is negative, I dig. I dig for 1. Okay, so in this case here, all of the orientations are positive, except for that one, the one on the right. And that's why I built one above that one, but then I dug again to go down. Okay, and this is the filling shape. So of course, sometimes if I have more negative orientation than positive orientation, I can build holes. Right, so here's a more complicated filling shape. Okay, so this is the tiling on the left, this is the tiling on the right, and I've built this, and because of all these negative things, I have a bunch of holes down here. Right? And this is my filling shape. This is the complicated filling shape. Okay, just given by these tilings. All right, and so the result that we end up showing, and these filling shapes really represent the distance between two different tilings. Okay, so I can actually compute the distance between two different tilings just looking at this geometric object that's naturally related to these two tilings. And the volume of what I get is exactly the distance between the two tilings. Okay, so if I have negative volume in this, I have to add up the positive volume with the negative volume. Right, I want this to be a symmetric function. Right, if I change the order of the two tilings, my filling shape is different. But it's just the plane reflection. Okay, and this is the volume. This volume is the distance. So that's what we end up showing. And that's very nice, because that allows us to give us a formula to be able to compute distances between tilings. Right, so you can actually see it. Okay, so here's an example, is that, well, if we have a given shape, we can try to find the largest filling shape we can possibly have. And that's going to be the diameter. Because the largest filling shape you have, the furthest two different tilings are apart. Right, so here are the optimal filling shapes for the Aztec diamond and for the square. Okay, so that's what they look like. You can't possibly get a better filling shape than that. Right? So this allows us to compute these things. So as an example, so for the square, this is what the diameter is. The diameter is n cubed minus n divided by 6. We get an exact formula. Okay, does that, for the Aztec diamond? And what I've shown you here are the diametrically opposite. These are the diametrically opposite tilings. Okay, this is exactly what they look like.
What was the insight dimension-wise? Go to the flattening dimension-wise.
Right. That's a very good. So that's really, in some sense, that's not us at all. That's Thurston's whole input into this. So his idea was to look at something that he defined as height functions, and it's not exactly this, but that's where that intuition came from, to try to look at this as a larger shape, as living in. Exactly. Good. Exactly. Right. Okay. So the diameter of the flip graph of this guy is also given by this nice formula. Okay. All right, so let me, again, a last time, hit you with the same thing over and over again. So I'm really pushing this motto to the most. I'm going to hit you with another problem where, again, we're going to look at the same type of things, and we're going to do the same type of counting, and we're going to do the same type of whatever. I mean, I'm going to be relentless with you, okay? So, but this is the last one, I promise. Okay, so here's yet another example of this type of situation. So this one is related to triangulations of polygons. So I take some n polygon, some regular polygon, Euclidean polygon, and I consider all possible triangulations of this polygon. Okay, so for instance here, you have hexagons, right? And these are all the different possible triangulations of hexagons that you can see. And I relate two hexagons by an edge, I create a graph, if I can do a flip. That means I have two triangles that are glued together, and I replace this diagonal here with this diagonal here. Right, so this is an example of a flip that you see there. And if you look at this picture carefully, so this picture here is from an article from 1988. This is the flip graph of a polygon. So we get a graph. Vertices are triangulations. Edges are given by flips. Again, we have a graph. And this is what the flip graph of a hexagon looks like. Okay, they drew the whole flip graph in their article in 1988. This is what it looks like. Okay, you can sort of look around at what it looks like. And they proved things about this graph. Okay, so what did they prove? They proved exactly. So, I mean, first of all, this sort of a classic exercise in combinatorics to count the number of triangulations you have. And the Catalan number appears. So those who know what the Catalan numbers are, that's great. So they appear in here. The n minus 2th Catalan number, that's the number of triangulations. Right, they appear. And, right, so that's one thing. And then they looked at the diameter of this. And what they proved, this is in 1988, they proved that the diameter of this graph is 2n minus 10 for large enough n. So this is a typical mathematical statement that from the outside world people start shaking their head, is that there's some n, we don't know which n, but for which the diameter is actually equal to this. Right, so do we know that the diameter of this graph for n equals 168 is this? No idea. But we know that there's some n for which it is, right, for large enough n. Right? So this is their result. And there's very interesting ideas that come into this. And very much more recently, in 2012, Lionel Pournin proved that the diameter is equal to 2n minus 10 for all n that is greater than 12. So he made the result more precise. And what's interesting is that his proof is really very similar to the proof I gave you. I mean, much more complicated, but in ideas, very similar to the proof that I gave you for the 2 by n rectangle, exhibiting two triangulations that have certain properties, and to get from one to the other, you have to make these transformations. It's morally the same type of proof. Okay, so what do these graphs look like otherwise? So for larger n, and this is, I'm just going to show you a few pictures. This is coming from some discussions we've been having with Marc Bell and Lionel Pournin about what these graphs look like and sort of playing around with them. Try to visualize them. What do these things look like? And so this is, for example, the graph when n equals 8. And you can play around with this, and you can try to move the vertices around. And we applied some algorithm that we found in a program called Gephi that had been developed by Yifan Hu. And this is sort of what the graph looked like, okay, after this algorithm. And we're like, no, okay. The point is that what you see here, this is the flip graph of an octagon. And do you see the octagon here? It's kind of, the points are sort of put in place of an octagon, right? There's sort of 8 sides to this. And this makes sense if you think about it, because the flip graph, if I have a triangulation of an octagon like this, I get another one by turning it, right? And any one of these turns or any isometry of the octagon should appear somehow in the graph. So there's a relationship between the symmetries of the octagon and the symmetries of this graph somehow. So we're starting to see the symmetries. And what really surprised us is if we went a little bit further, so here's n equals 11, so this is becoming sort of at the limit of what our small computers can take. And so, well, we applied the same algorithm, and we got something like this. This is kind of cool. So this time you see, so if you count the number of sides, there's really 11 sides. So the algorithm is clearly detecting the different symmetries of the original 11-gon. And so if you look at all the symmetries and you get rid of the symmetries and you look at what's called the quotient graph, but the point is that you want to look at these things but up to symmetry. So you apply all these different symmetries, what you get is something that's really ugly. So I guess I'm going to stop here. I guess the moral of this is that sort of symmetry is what makes things very nice, but once you get rid of the symmetry, it's not so nice anymore. Thank you very much for your time. Groups of what? Sorry, crab eaters?
How does this allow you to conceptualize or see emergent links or relationships?
Okay.
From these images?
Right.
Ask computer science graph theory, how do you do graph?
Right. So very good question. Of course, the real answer is I have no idea. Maybe the longer answer that I would give, if I need to justify this for a grant or something like that, right, would be something more along the lines of when you play with these. In this case, we're playing with large graphs, right? And as you say, graphs can be used to encode all sorts of things. And there's sort of a variety of methods that you can try to use to try to look at these things. And so from my point of view, I'm coming from a world where generally you look at sort of infinite objects. And I'm looking now at these graphs that are sort of finite graphs. And what happens is that you see many of the same things that go on in the world of, let's say, geometric structures, infinite geometric structures that you see that go on in the world of graphs. And one of the reasons for that is, like, for instance, the Rubik's graph. Okay, so it's a finite graph, but it's essentially infinite. I mean, Okay, for all practical purposes, it looks very much like an infinite type object. And so the type of intuition that you're getting coming from other areas and looking at this type of thing can always be interesting to try to navigate in that. And I think the example of what they did with the Rubik's graph is very nice, because it's a mix between sort of computer science and math, and you really needed both to be able to tackle this problem. Without one or the other, you wouldn't be able to. So
will I get insights into algorithmic efficiency?
For instance, I mean, certainly, probably not what I'm doing, but what people are doing that is sort of related to this, certainly. Yeah, I would certainly think so. Absolutely. Sure.
When I look at this picture, this looks like a network on the web. So you have produced all these graphs. Diameter is one property.
Absolutely.
Like expand that graph. First I can measure. Has anyone computed that?
No. That's a very good question. So, So, for instance, there's a whole, in computer science, there's a whole industry of usage for graphs that are called expander graphs, right? And so it's always interesting to have new examples of expander graphs, things that you can sort of look at. And for instance, these graphs here, properly normalized, could very well give you a sequence of expander graphs, but it's not known. It's absolutely not known. And you're right, the diameter is only one property. But there's lots of things that are not known about these graphs. I mean, the diameter is now settled recently, but there's lots of other things that are not known at all about these graphs. And this graph here, this quotient graph, as far as I know, nothing is known. No, I mean, if we did, then we might know whether it was an expander family. Right.
Is that like formation of this kind of cycling would be a clue that they are actually connected, or?
Right. That's a good question. So at least in certain cases, we're able to count the number of different components that you have using these cycles. If you just have one hole, for instance, you can count the number of connected components using these cycles. And presumably, you can get some type of distance formula on shapes that have holes in them using these cycles as well. Yeah. Very good question, yeah. Yeah.
Can you give a rough heuristic argument why the distance
Oh, I mean, it's their proof. I mean, what they use is they use hyperbolic polyhedra. And they used sort of representing this graph as vertices of these hyperbolic polyhedra. And then they got estimates, and the estimates sort of came up with comparing volumes of things. But, I mean, that's probably a very useless answer. But okay. Okay. Right.
The question is, how does this help us look at it from a real world point of view? Is there another example that we can use to sort of illustrate the idea, or at least tell us, you have this particular situation, and if I say that the distance is going to be 3,
Mm-hmm.
then it takes basically 3 steps for us to convert this situation to this situation.
Right.
So how are we going to use that idea?
Right. So, I mean, so there's sort of the point of view, if you have some type of geometric intuition as to where distances are coming from, then from this you can deduce algorithms to get from one tiling to the other. Then in terms of the real world situation, I mean, I don't know any situation where people really had to compute distances between tilings per se. Right? And in general, the point of view that I mean, but I'm not saying that there isn't. But In fact, I mean, there are real-world applications to this stuff because it's actually related to dimer theory, and dimer theory is related to all sorts of other things, including like mathematical biology now and things like that. But I just don't know anything about those real-world applications. But the point of view that we tried to portray in all of in the book app that we wrote and the things is that we tried to go from the point of view of trying to create an intrinsic interest, as opposed to advocating mathematics as a wonderful tool for other things, which it really is. But I'm just saying that our point of view was to try to create an intrinsic interest with this type of thing. So that's the point of view I'm taking. But again, that's a choice. Right. I mean, sure. Yeah, absolutely. I mean, the discrete can help you for this type of thing as well. So, for instance, we had a speaker at the conference this week called Feng Luo, who's talking about ways of using triangulations from getting from one image to some other image. But the original, what you're trying to do is you're trying to estimate some type of distance, sometimes between objects that are continuous, and you're approximating them using triangulations. And this tells you something about something. And in general, sort of in the more general deformation theory, discrete structures can tell you things about continuous deformations as well. But you're absolutely right. I mean, the goal would be to it goes beyond just the discrete. Yeah. Right. Exactly.
Any more questions?
No. Actually, so the Rubik's Cube graph is kind of funny because if you just look at the graph, then every vertex looks exactly the same. It's a homogeneous graph. You can take a graph and move it somewhere. You can move, there's sort of a symmetry of the graph that takes any vertex to any other vertex. So the symmetry group of the graph is transitive. So in that sense, there's no particular points if you just look at the graph itself, but you've chosen a home configuration. You've chosen one that's the one that you got in the box. Right? But that's an arbitrary choice. Right.
Well, Professor Parlier has given us a beautiful exposition of and a very interesting topic in mathematics on something rather simple, at least to me, seemingly simple like Rubik's Cube, to some very, very sophisticated mathematics. And in a way, I'm actually glad I did not become a professional tennis player. I think mathematics has benefited greatly from him. So before we end this session, I'd like to present Professor Parlier with a token of appreciation from the Institute for Mathematical Sciences.
Thank you very much. Thank you. Thank you very much.
It is a IMS coffee mug. I hope he drinks a lot of coffee to improve my
I do.
And I also like to take this opportunity to thank the Ngkombeng Memorial Fund for its general gift in enabling our institute to organize this series of public lectures. And thank you for coming.